Hi everyone, how's it going? This is Siri and I'm back with another PyTorch video, and in this video we're going to be continuing our discussion on how we change, update, / estimate W and B, which are our weights and biases, so that our loss reaches a minimum. So in the past few videos and in the next couple of videos, we're going to be dealing with an example that has a linear relationship between its inputs and outputs. So as a refresher, we're doing a temperature conversion, and we went through a lot in the past 3 or 4 videos, and just talking about the learning process, connecting it to what Johannes Kepler thought about, or did with his laws of planetary motion. And we introduced this temperature conversion example between a temperature of unknown units and a temperature of known units, and we converted it to tensors, and we figured out this relationship. We defined all of our things, and we initialized the parameters, and now we're trying to change and update it. We connected it to an example of a number guessing game, and connecting that to our loss function. So which direction do you need to update the parameters? Do you need to increase it or decrease it in order to get the representation of the data that you want? So we went over this several times in my past couple of videos, so I would highly recommend watching those before jumping to this one, because there's a lot of background information that we've talked about. Okay, so there are different ways of representing your data, and there's only one way that's it's the same way of representing your data, except different parameters give you different results. So for example, if you had a line which models our relationship that we have between our input and output, which is linear. If you have a certain slope and a certain y-intercept, we're going to have a certain line that might represent our data. But if we change those up, we have a new line that doesn't represent our data anymore. And so that just shows you how important it is to get your parameters, which in a linear relationship sort of situation are only your W and B. It's so important to make sure that they're accurate, that they actually, model your data. And where did we leave off? Well, we defined a rate of change of loss, right? That's how we're going to change our parameters and adjust them to make sure that they're right. And so we did a rate of change of loss with respect to W, and we did the same with our bias. And that's how we're updating it, right? So we could have also said that W minus equals learning rate times that, or, but I just want to be really explicit here. And we have a learning rate because we need to update our parameters slowly. We can't just, subtract the loss of, we can't just subtract the rate of change. We need to scale it down really, by a lot, and we need to make it really small, because we don't want to be updating our parameters by too much, because if you'll end up with in a situation like this where we are trying to guess a number and we're at number 9, that's our guess, and then we went too far up, we updated it too much, and now we're too high, so we're further away from our goal. And so we need to not update it super slowly, because then that's going to take forever, but, at a reasonable rate, and that's the learning rate. Okay, so in this video, we are hoping to, change up this delta, by, you change it up into, a derivative. And I was saying in my past video, at the beginning of a calc class, you might learn about, like changing it up or getting super duper close to the point to find the like the secant line that, you know, really matches and approximates that like slope. But then you learn something new and you say, hey, I don't even need like 2 points that are super close. I can just take the tangent line. And you know, so it's like that. Instead of taking a really small like delta value and changing up your weights and bias to get that rate of change, you can just take the derivative. So yeah, that's where we're at right now. And so we're going to be taking the derivative of the loss with respect to the parameters. So we're going to be taking the derivative of the loss with respect to your parameters. And if this is not familiar to you, I would recommend watching a few videos, just fairly introductory videos, and maybe I can sum up the idea in just a few seconds here. Like if you have you know, a curve that's not a line. In this case, our line has a specific actually, no, we're taking the derivative of the loss. The loss is not a line. Okay, so in our case, we're taking the square of differences, of the difference between the actual and the predicted value, and so we have this sort of curve, and you know, you can take a point and find the slope at that one point. And I know you need 2 points to get a slope, but you know, you just find the tangent line to that curve, that spot on the curve, that point on the curve, and you know, that slope of that tangent line is the derivative. So we're going to be taking the derivative of the loss with respect to your parameters, and yeah, that was meant to be like a refresher. That's not like a high level. That's not like, we're not going deep into what derivatives actually are, because you might want to learn more about the applications and why we use them, because they're important to, you know, learn about what's actually going on behind the scenes. Okay, so we take the derivative and we take the individual derivatives. Okay, so we have you know, we have a derivative for each parameter. Okay, and in this case, we have 2 parameters, our weight and our bias, and you know, we're going to have 2 derivatives for for our situation because we have 2 parameters. Okay. So, and then we put them in a vector in a neural network. So when you have some nonlinearity to this, you know, modeling of data, you are going to have a lot more parameters because you're not just dealing with, you know, a slope and a y-intercept. You're dealing with so many more things. And so when you, like, that's not to say that linearity doesn't have an important spot in neural networks, because it definitely does. That's a key component to neural networks. But the things that make it interesting are that nonlinear aspect, or is that nonlinear aspect. And so when we have tons of parameters, we're going to have a large vector of derivatives. And so that vector we would call a gradient. Okay, so a vector of derivatives you would call a gradient. Okay, and so that's where we get our name for this algorithm for finding a way to update our parameters. That way we call gradient descent. Okay, so maybe we should bold this. Yeah. Okay. So great. So in order to find the derivative of our loss with respect to the parameters, we are going to need the chain rule. Okay, and the chain rule, just as a refresher, I would definitely recommend watching a video on the chain rule if you're not familiar with it. And I'm also planning on making some calculus videos for this, whole machine learning area, and so you can look forward to that. But for now, just learn more about the chain rule, just like a brief introduction maybe. So if we have a function of a function, so we have a composition of functions, the derivative of f of x is dependent on the derivative of g of x. So we have the derivative, we have like f prime of like whatever g of x is, and then we multiply it by the derivative of g of x, and we're not looking at it in relation to f of x, we're just looking at g of x in isolation, and we take the derivative of that. Okay, so that's the chain rule. So how does this relate to our example? Well, we have, okay, actually not our example, but like, just machine learning in general. So we want to take the derivative of the loss with respect to your parameters. But remember what the loss function is, right? We take a look here. Yeah, we define the loss function. Okay, and we first need to take the derivative of the loss function with respect to its own inputs, okay, which is TP and TC. Actually, it's not TC, it's TP. Because when we actually go down to our implementation here, and when we're finding the rate of change, we're taking, like you see this, like it's a loss function of the model, okay? And this model is, like the output of the model is TP. So this is what we got to do first. First, we got to, take the derivative of the loss with respect to TP, with respect to its input, and multiply it by the derivative of g of x, which in our case is going to be the derivative of the output, right? Because this is TP, so it's the intermediate, portion. So TP with respect to its input, which is the parameters, right? So that's how so instead of looking at the loss now, so when we take a look at the loss, we have TP, and when we look at TP, right, our prediction, it's actually coming from the model, so that's based on the W and the B, so those are the actual parameters. And so let's go on to actually defining that in some code here. So first, okay, the loss function is the square of the difference between the predicted value and the actual value. And yeah, we went over that, right? So let's say def d loss fn, so d meaning derivative, and so we are going to have TP and TC, okay? So this is the actual value, and this is the predicted value. Actually, you need TC, right? So I kind of take that back when I said, oh, we don't need TC. We do, because that's, you have to take the difference. So we have D difference, like D and then square diffs. So that's going to be 2 times TP minus TC divided by TP dot size. Okay, 0, and so here we have the derivative, okay, and we're going to be dividing it by each element. And so let's just return the square difference, the derivative of the difference, the derivative of the square of the difference. So let's just return that value. And we're all good. And don't get confused by this part. We did something similar above when we did something with a mean. So yeah, here, this is a tensor, right? So we need a scalar value. And so that's why we need to, take the average of each of the elements in the tensor. Otherwise, we're gonna have like an entire tensor full of values that we could interpret as our loss, but we just want one single value that we can use. Okay, so that's what we're doing, and we're returning that. And also, let's apply that. So we're applying the derivatives to the model. Let's have D model, and let's do it with respect to the weight. TU, W, and B, and return TU. And def D model of DB, TU, WB, and we're going to return 1. And what are we doing here? Why are we returning TU and 1? Well, if we take the derivative of W times TU, okay, so the whole loss part is, the input, which is TU, times a slope, which is our weight, plus a bias. So if we just look at the, the W times TU part, we get a derivative of TU because, the weight is the variable and the TU is constant because we just have an input. So that's our output. That's our derivative. And we have, just the B part. B is also, just like weight it's like you're updating it. And so, if we just have X, which is our variable, just like, B is, the derivative of X is just 1, because if you have Y of X, the slope is 1, because it's linear, right? So, yeah, so this is the derivative of the loss with respect to, actually, this is the derivative of the model with respect to W, and this is the derivative of the model with respect to B. Okay, so, yeah, and let's define our gradient. Our gradient is our vector of derivatives. We have 2 derivatives. Let's put them in a vector, and let's see how that goes. Okay, so what we're doing here is we're defining a gradient function. Okay, vector of derivatives. So let's say def grad fn, so gradient function. So now we have to take in everything. So tu, tc, tp, w, b, and d loss, dtp, d loss, dw, d loss, db, and we're going to return something. So this is the loss with respect to its input, its direct input, okay? And its input is based on the weight and the bias. That's like the W and the B is like the G of X part of our f of g of x. And our f of x, our direct input to f is just g of x. And so our direct input to our loss function, which is the f, is the predicted value. So let's take that derivative. So we have d loss fn, tp and tc. Okay, so this is the first part of the chain rule. And we have d loss with respect to the weight. So d loss dtp times the d model dw tu comma w comma b. So this is the chain rule that's happening. We're taking the actual derivative and we're multiplying it by the derivative of the inner function, which is the model. And we're doing the same thing here, except instead of d model dw, we're going to say d model db. Okay, and we're going to return torch.stack. Okay, and dloss dw.sum and dloss db.sum. Okay, so this is our vector here that we're returning. And all stack does is that it concatenates to, tensors along a certain dimension. Okay, so we can have as many tensors as we want here, but since we only have 2 parameters, we only have 2. All right, and we're going to be performing updates to this iteratively, and that's this whole training process, which we're going to be talking about in our next video. We're going to be, defining the training loop and all that stuff. So, and we're going to do it until W and B stop changing, because that's when we know we've minimized our loss, and those are the exact values of the slope and the y-intercept that we need to best represent that data that we have. Okay, so I hope you guys learned something new, about how derivatives actually play a role in this whole machine learning process, and we'll see a much better way to do this later using PyTorch's AutoGrad. So it'll do it, it'll have a nice little trick to it, which we're going to be talking about later. But yeah, I hope you guys learned something new today about gradient descent and all of that. And don't forget to like, comment, and subscribe.